We've already seen a Canter set in one form, but this will be a different description and of equivalent metric. Okay, it will be as a set, it will not look identical, but almost identical. Namely, we look at the subset of the unit interval. So let's take a unit interval here, maybe a straight line, so that we have 0 at one end and 1 at the other end. And we'll first write the set description and then look at a picture of this. So the set description K is the set of all sums 2an by 3 to the n. N goes from 0 to, well, I want 1 to infinity. Okay, n is 0 will mean I will get an integer, which we don't want. So an is in either 0 or 1. Okay. So we are looking at the sum of numbers whose ternary representation, that is base 3 representation, has only zeros or 2's. That's what this description is, and it's quite easy to prove it. So we'll see a lot of elementary things in a relaxed way. So this, so to start the labeling, suppose we have 0 here and 1 here, okay, and then those which, okay, so if we look at the first term a1, it's going to be either 0 or it's going to be 1. Okay, and if it's 0, we can see that we'll lie between 0 and 1/3. And if it's 1, we'll lie between 1/3 and 2/3. 2/3 and 1, between here or here. So we're going to be either in this set or we are going to be in this set. Okay, and these things and a whole bunch of things are based on some simple inequality. The inequality is, if I look at the sum, so we use throughout the following proposition, which is just summing geometric series. We want to say this is between 0 and 1, but more generally, if I look at sum from n equals k to infinity of 2an by 3 to the n, we are looking at the terms from k onwards of these. That is less than or equal to, so the absolute value, well, we'll specify here. So I'm looking at 0 is less than or equal to this, which is less than or equal to, well, if k was 1, this is 1. In general, it's 1 over 3 to the power of k minus 1. If an belongs to 0, 1 for all n. Okay, so if we have such a sequence, we'll use this for differences between sequences as well. So hence k is contained in the 0, 1, interval 0, 1. And we do get a point 0 where all these are 1. And we do get a point 1 also. And the point 1 comes about, so the point 1 comes about when I take all an's to be 1. Okay. So we have the fact that representations with any base are not unique, but that doesn't matter. There exists a representation without ones. Okay, so that is points in 0, 1, the interval 0, 1 with base 3 representations without the digit 1. So with 0 and 2 only the base 3 representation. Points which have such a base 3 representation. If there is a non-unique, at least one of the representations must be of the form. So hence k is, so in particular we have seen k is less than or equal to 0, 1 using this inequality. And from these, okay, for what happens, so the first digit 0 will mean that your sum is at most, so you're looking at the sum from k equals 2 onwards, so it's at most 1/3. Okay, so if first, so if a1 equals 0, then this sum 2an, n equals k to infinity by 3 to the n, this is also the sum n equals 2 to infinity. Sorry, n equals 1 to infinity is also 2an by 3 to the n, sum 2 to infinity, which is less than or equal to 1/3. Okay, and if a1 is 2, then the first term itself is 2/3, and so you're bigger than 2/3 and you're less than 1. So you're going to be either here or here. What about if we take the second digits? Well, suppose the first digit is 0, then the second digit is either 0, second an, so a2 is either 0 or it's equal to 1. If it's 0, we'll see that we are in this subinterval, going up to 1 over 9, and between 2 over 9 and 3 over 9, which is 1/3. So we lie in this set or this set. And similarly, at the next step, we lie in this set or this set. And the whole process keeps repeating depending on the nth digit, what the nth digit is. Okay, so in general, okay, so given, let's take the proposition. Given, let's say a1, an, not fixed values, all of them in 0, 1. If an is a sequence, or maybe I'll call this k, an is a sequence in 0, 1, such that ai is ai naught for all I less than or equal to k, then the sum n equals 1 to infinity of 2an by 3 to the n, this belongs to the following interval, which will give it a name. So first of all these numbers are greater than or equal to 0. So if I look at the sum from n equals 1 to k of 2a n naught by 3 to the n, that is a lower bound clearly, because everything else is positive. But we also know that this set, if we look at this, which is 2an naught by 3 to the n, the same number, plus 1 over 3 to the power of, we should be a little careful here, it's either k or k minus 1, so we can check, so it would be k minus 1, I believe, because if we fixed only the first, or if we fix the first one, we get the interval k. Sorry, so we vary from k onwards, so we get 3 to the k. Okay. So given these points, we have a sequence here. So okay, all these are proved by summing geometric series, so we are not, I won't prove this in detail. So the first n quantities determine an interval that you lie in, which I'm going to call k of a1 an, and this is contained in k, a0 a1 not a0 k. This is contained in the Canter set k. This is union over all a1 naught a1k. So when the upper subscript indicates which level we are in. So for level 1 we have both the interval on the left and the right. Level 2 we have the interval on the left. We have the interval this and this. Also we look at all finite sequences of a given length. We have associated to them closed intervals, which we can see are disjoint from each other. And indeed, playing around with this inequality, we can get a good control over the distance. So firstly, at level 0, you see if you have if you are both on the same of these sets. So the first set here is what we would call k1, and this set is called k2. If you are in 2 points in k1 are a distance at most 1/3 apart. Similarly, 2 points in k1, sorry, this was called k0 and this was called k1. 2 points in k0, 0 or the same set at this next level are a distance at most 1/3 squared apart. And conversely, if your distance is strictly less than 1/3, you must both be in k0 or k1. Okay, so just using the same inequality again and again, which is obtained by summing geometric series, we can observe that if I have two sequences, an and bn belong to k, so I'm abusing notation and associating sequences with points. Okay, so if both of them belong to points k, a, 1, 0 a1k. Then the distance between sigma an. Okay, so this is also the set of all sequences an such that ai equals ai naught for all I less than or equal to n. Okay. Okay. So let me, I should ideally use different notation for set of all sequences with a given initial segment or for the points they represent, but it's clear from the context, so I will just use the same notation. I should maybe put a hat on this too. Let's put a hat, why not? Okay, so let k hat of a10, ak0 equals these things. So this is a sequence of in 0, 1 of zeros and ones, so that the initial segment is given. So if an and bn are both in initial segments, that the distance between 2an by 3 to the n and 2bn by 3 to the n. So the first n quantities agree with each other. So if I'm looking at the corresponding points, so first k points agree to with each other. This is less than or equal to 1 over 3 to the k. Okay, so if 0 agree, it's less than or equal to 1, which is consistent. And conversely, okay, so both of these is follow from the inequality, as I said. If distance between some 2an by 3 to the n and 2bn by 3 to the n is strictly less than 1 over 3 to the k, then, so for example, if distance is less than 1/3, you must be in the same half here. Okay, then what we have is that there exist, or it's cleaner to just say that ai equals bi for all I less than or equal to k. So then the first I digits agree, first k digits of these agree. Okay, so if they are here, we will prove these very briefly to illustrate how to work with the sequences. It's all quite elementary stuff, but quite relaxing to prove these things. So since A is simpler than B and A and B are very similar, I'll just declare A to be an exercise. Okay, so B, if we have two sequences an and bn, they belong to the same k of a0, a1 naught up to ak naught. Then what we know is, I mean, belonging to the same division is just the same as saying that aj equals bj for all j less than or equal to k. Okay, so being in the same group, we are partitioning things by saying that the first k digits are equal, they are there. Okay, therefore, if I look at the distance between these two, which is just the sum of k equals, n equals 1 to infinity of an, 2an by 3 to the n minus sum n equals 1 to infinity of 2bn by 3 to the n. This is less than or equal to the sum n equals 1 to infinity of 2 times mod an minus bn by 3 to the n. So far we have just rewritten it. But notice the first k terms are equal. This is sum n equals k plus 1 to infinity of 2 times mod an minus bn by 3 to the n. And notice that this an minus bn is either 0 or it's 1. So by our lemma, this is less than or equal to 1 over 3 to the power of k. I believe it was k that we got for k to the n minus 1, yes. So this is sum from k plus 1. So these are equal to k. So this is the bound on these. And how about C? Suppose, so if points are in the same partition, the first n digits agree, then they are actually close to each other. But conversely, suppose we have something slightly sharper. So suppose distance between, or I'll write it as mod for the consistency. Suppose mod n equals 1 to infinity of 2an by 3 to the n minus 2bn by 3 to the n is less than 1 over 3 to the k. Now this is strictly less. What we want to show is that the first k digits agree. Okay. So let j be the smallest index such that aj is not equal to bj. So this exists unless the sequences are exactly equal, and if the sequences are exactly equal, there's nothing, then their first n digits are true. Okay, so let j be the smallest index such that this happens, and without loss of generality, assume that aj equals 0 and bj equals 1. Okay. Therefore, what do we know about the sum? So sum n equals 1 to infinity of, let's look at this quantity, 2bn by 3 to the n. We'll break it into 3 parts. So there is the sum n equals 1 to j minus 1 of 2bj by 2bn by 3 to the n. N is just the index. Okay, then there is another term which is just at j, but there we know it's 1, so that's why for emphasis I'm keeping it separate. Okay, so plus something else, j minus 1. Okay, but instead of writing that something else, let me just note we have an inequality. This is less than or equal to this. Okay, and what about the sum of j? Sum n equals 1 to infinity. The reason I bounded this is that we know that one with b bigger is going to be a bigger quantity, so we'll just lower bound that and upper bound the a, and this will give us a gap between them. So 2an by 3 to the n. This is, well, sum n equals 1 to infinity. Oh, I'm sorry, I got this inequality wrong for just sloppiness. We are lower bounding the quantity with b's and upper bounding the quantities with a. So n equals 1 to infinity 2 to the n. We can break it up into again 3 pieces. N equals j minus 1 to an by 3 to the n. But notice these two quantities are equal, because an's and bn's are equal up to j minus 1. By the way, they could be 1, so this could be an empty sum. And then there would be a 0, and then there will be the sum n equals j plus 1 to infinity of the 2an by 3 to the n. Okay. As I said, this is elementary but quite relaxing. So these two are equal. So this is greater than or equal to, I will just write it, rewrite this, n equals 1 to j minus 1 of 2bn by 3 to the n. So both of these you could identify with that an naught as we called it. Okay, so suppose these two agree up to n, and greater than or equal, sorry, I don't want to bound that way, I want it less than or equal to. The 0 term crucially is just 0, while here we had a large term, and then the final term is 1 over 3 to the j. Okay, so therefore what we know is that sum n equals 1 to infinity of 2bn by 3 to the n minus the sum infinity of 2an by 3 to the n is greater than or equal to a positive quantity, 1 over 3 to the power of j. Because here we had 2 over 3 to the j, here we had 1 over 3 to the j. So all we have done is said that this term bj dominates over whatever the a's can be. Okay, but on the other hand, we have this inequality which is telling you that 1 over 3 to the k is strictly greater than this. Okay, so this implies that j is, so 1 over 3 to the k is bigger quantity than 1 over 3 to the j, which means that j is strictly less than k. That is a1 up to ak is, I'm sorry, j is strictly greater than k. Okay, so it means, so, but then we know for up to j we agree. Everything less than j we agree. So a1, a2, ak is b1, b2, bk. So we have a nice control over the metric and the partition of the Cantor set. Okay, so this control of the metric and the partition of the Cantor set will let us show that this metric is equivalent to the other one we defined. So up to the fact that we had to interchange less than or equal to, the previous ultra metric we defined, we looked how far two sequences agreed and looked at 1 over 2 to the k. But in terms of being big or small, looking at 2 to the k and 3 to the k make no difference. And while we don't have a sharp thing here, in one case we had one less than and one case less than or equal to, again in terms of epsilon delta it makes no difference. So from this we can see this topology is equivalent to the previous topology. We can see a whole bunch of other things which will be left as an exercise following this video. But now I want to instead target something very interesting we get out of this, which is space filling curves. Okay, so we'll use the Cantor set, okay, following Viro and Co's book, to construct this remarkable object which is a space filling curve. So a space filling curve is a surjective continuous function f from 0, 1 to 0, 1 squared, etc. So you could try to fill up a sphere instead or various objects, but it fills up a higher dimensional object from 0, 1. And lots of space filling curves exist, and they are based on the fact that even much larger set of spaces are images of Cantor sets. When we come to compactness, we will see this. Okay, but for now we want a concrete object. So here we had the Cantor set. So first let's construct a map. Okay, so map from k to 0, 1. Okay, so this is a map which will send, let's call it phi, mapping k to 0, 1. Well, phi of, I'll make a comment as soon as I write the definition. 2an by 3 to the n is by definition sum n equals 1 to infinity. We'll turn the ternary representation into a binary representation, an by 2 to the n. But so binary representations are not unique. So more than one point will go to a point where the point has a non-unique binary representation. We'll see a picture of this in a moment. But first, to clear out a logical issue, one of the corollaries of our part C, which said that if 2 points were close to each, part B, if agreed at the first j points, no, it's part C. If 2 points were close, then that is 2 points like this were close, then the corresponding ans agreed up to j, depending on how close they are. So if 2 such points are equal, they are close to any scale, so the whole sequences must be equal. So injectivity, which you can prove directly, is an immediate corollary of what we proved previously. So this is well defined. Yeah. So throughout I'll be sketchy, try to point out the main ideas, and we'll have an extended exercise which involves showing this. So what kind of map is this? Well, here's the interval, and what we are kind of doing is filling in the interval in the Cantor set. So in the Cantor set, we have this part. So we have this region and this region. What we'll do is we'll map both these points to the point half instead, which is the midpoint of the interval. Okay, so it's easier to write a Cantor set in terms of the region that's excluded. Okay, so one of the things you'll see in the exercise, or you can read about it, is that the Cantor set itself is an intersection of these closed intervals. So it's a closed set. And what you exclude are various open intervals. For example, we will exclude this orange region. So what we'll do is we'll pinch out the part that's excluded. We'll also exclude this region. So these two orange endpoints go to a single point here. and so on. So we just turn the binary into the ternary. So what we can do is glue together these points, and what you get is an interval. So this is what this map is. Okay, so why is this continuous? This is continuous from the previous lemmas. Okay, so let me just say, so this is continuous as, let me just point out the main inequality and leave the epsilon daltonics to the viewer listener. Okay, so continuous as, if I have sum of 2an by 3 to the n, and if I have the difference between these two sums less than 1 over 3 to the k, so I've taken my delta of the epsilon delta to be less than 1 over 3 to the k, then this implies that ai equals bi for all I less than or equal to k, which implies, with a binary version of our other lemma, it implies that sum of an by 2 to the n equals 1 to infinity. If I look at this difference between the corresponding binary numbers, bn by 2 to the n, again summing geometric series will tell you this is less than or equal to, since we have an agreement up to k, it will be 1 over 2 to the power of, I believe it's k minus 1, or is it k? Well, if I had agreement up to 0, I would still get 2 to the power of 0. So yeah, so it's 1 over 2 to the k. So this happens. So given epsilon, you find k which is less than this, maybe strictly less than, and then find a delta corresponding to 3 to the k, and that will tell you that if things are close. Oh, I should emphasize that this is of course phi of sigma 2an by 3 to the n. So this is the difference between the images. So this is a continuous map which goes from k to k squared. Okay. Now to get a space filling curve, we need another thing, which is we can take a Cantor set inside a square. We do exactly the same thing, but this time we'll start taking intersections, not of intervals, but of maybe of squares like this. So I take this square, this one, and this one. And then we further look at this square inside it, and this square, etc. So formally this is exactly the product. So formally what we have is k squared k squared, sorry, writing with lines is not ideal. So k squared is the set of all pairs 2an by 3 to the n and 2, or let's call them xn, and 2yn by 3 to the n, such that xn, yn belong to 0, 1. Okay, so this is contained in 0, 1 cross 0, 1. Okay. And so what happens, so this is exactly these squares. It's pairs of numbers, both in the Cantor set, which is contained in this. And we also have a map, let's call it psi, from k to k squared. Oh, I should say this is phi is onto. This is because every element has a binary representation. Okay, phi is onto. So you can use the result that everything has a binary or representation. If you're not happy using that, prove it and use it. Okay, so now we are going to construct this onto and continuous, and use an old trick due to Cantor to make a sequence into two sequences. This is how you show pairs of integers are countable. Namely, we'll map sigma an by 2an by 3 to the n equals 1 to infinity, psi of this, which is corresponding with just the sequence, to, I look at the odd sequence and the even sequence. So I look at sum n equals 1 to infinity to a to the power of 2n by 3 to the n, and sum n equals 1 to infinity of 2a to the power of 2n plus 1 by 3n. In fact, you would see easily that this is a bijection. Well, why is this continuous? It's a matter of 3 to the n versus 3 to the n squared. If I have 2 points which are close enough so that their first 2n points agree, for which you have to make sure that you take your delta as 1 over 3 to the 2n, then if I look at the odd and even subsequence, the first n's of those agree, and so the distance between those is less than 1 over 3 to the n. So given your epsilon, you basically take delta as epsilon squared. Okay. May have to just sort of do the rounding off, that is, you pick 3 to the n less than these and then take the 3 to the 2n on the left hand side. Okay, I've said this orally. As I said, it's an extended exercise to fill in the details, but this is easy. Okay, so these are all the ideas. Okay, so I've gone from k to the 0, 1. I'll call this phi, and I'll have another map which is like phi. So let me call it phi squared, mapping k squared to 0, 1 squared is surjective and continuous. Okay, so let's call this capital phi or something. Phi squared could be confusing. Capital phi, which is just the product. Okay, and namely I just define the sum of 2an by 3 to the n, sum of what I called xn, and sum of 2yn by 3 to the n. This maps to the binary representation, sum of xn by 2 to the n and yn by 2 to the n. Sum of yn by 2 to the n. So this is exactly what you would get if you apply phi on each coordinate. So we have a surjection which is onto and continuous. So what do these together give you? So by composition, have a surjection which is going to be, let's call it f sub k, mapping k to 0, 1 squared, which is continuous. Okay, so this already gives the main seeming paradox, because k seems one-dimensional, it's mapping onto a two-dimensional square. Okay, so k is here and k squared is 0, 1. By the way, k and k squared already give you a seeming paradox, right? A product of a space with itself was equal to the original space. Okay, and now we extend. So k is contained in 0, 1, and it has a bunch of holes. So here is 0, 1, and here is the square, and we already have a surjection onto it. We have something that fills it up, but that surjection is on a subset. Now from a subset you may not be able to extend to the whole space, but in this case you can, because it's a particularly nice subset. So what you have excluded are these open intervals. Okay, so how would we extend on such an open interval? Let me say this briefly. The brief explanation is that you extend by convexity for on 0, 1 minus k to get f from 0, 1 to 0, 1 squared. This is surjective and continuous. So these are called piano curves, or their images are called piano curves, because piano first constructed such an example. Its construction was a bit different, but it's the main idea of us having an infinite recursion was the same there. Canter sets make this infinite recursion particularly nice. Okay, so let me just briefly explain what I mean by convexity. I won't do it in detail because we need a detailed description of the complement of the Canter set. But the complement of the Canter set is exactly open intervals of this form A and B. Okay, and with A and B are both in the Canter set. So we have open intervals, A and B are both in the Canter set. Now from the earlier description of the Canter set, you will get this result. Okay, and the fact that K is the intersection of all those Ki's. Yeah, so now what we know is we already have f defined on A and on B, and we want to extend it to an interval. So on an interval, so namely, more concretely, 0, 1 minus k is the union of intervals, in fact, n equals 1 to infinity a n b n, with n bn disjoint intervals such that a n b n both belong to k. Okay, and then we can define it on the closed interval, and it will be consistent with the old definition. Define f from restricted to a n b n from in fact closed interval, from the closed interval a n b n to the set 0, 1 squared, which note is a subspace of the vector space, by f restricted to the closed interval a n b n of x equals, we have to see where the position is. So x minus a n by b n minus a n will tell you how far you are along that interval. So here's x, here's a n, here's b n. So we want to take convex linear combinations, and so when x is 0, we want it to be f of a n, and when x is 1, we want it to be f of so when x is 0, so we look at x minus, so I look at x minus a n by b n minus a n. This lies between 0 and 1. Okay, and so when this is 0, we want it to be f of a n, but that term doesn't turn up, so this is this times b n plus 1 minus this, and 1 minus this will simplify to b n minus x by b n minus a n of f of a n. So just to check, when x is equal to a n, this term is 0 anyway, and this is b n minus a n by b n minus n, 1 times a n. And when x is b n, then we get 1 here and 0 here, and you are always between these two. You are always a linear combination of these. So this is a convex set, and hence you lie inside this convex set. Okay, so detailed structure of the Cantor set will be an exercise, but given that we have constructed this really interesting object called a space filling curve. So just a couple of historical remarks. So generally speaking, when it comes to foundations of mathematics, up to at least 1920, you would have a phase where there was a bunch of state results. You would have mathematical results. Today we'll call them theorems. Earlier there were calculations or whatever else, and these would depend on lots of things that were obviously true. Now, one of these obviously true statements was you can't have a continuous onto map from a lower dimensional to a higher dimensional space. Then you discover that some of these obviously true statements are actually false, and so then you shakes up the foundations a bit. I said up to 1920, but in some sense it happened beyond that with algebraic topology, where the Hauptvermutung, as it was called, well, it wasn't actually disproved till a little later, but people could not prove it. It again turned out to be the false, and algebraic topology had newer foundations because of getting around the fact that you could not prove this statement. As it turned out, it was a false statement, so it was fortunate you could not prove it. And finally, when it came to so in some sense you can say that that's sort of happening at a higher level now again. Of course, it's not enough to say something is necessary. It also has to be possible, and it was possible to have proper foundations by the early 1920s. And now today in the small scale we don't have such contradictions, but on the large scale there is an issue with managing being correct in mathematics. And you can say that computer formalization of mathematics, which is now becoming possible and taking off, is the next stage of where things which are sort of left as obvious, or which we are obviously correct, or you use a judgment that they are correct, are replaced by being correct on more solid grounds.